Hello, welcome to my talk on dimensional analysis, Buckingham Pi theorem, the detailed advantages. In this talk, I will give a short summary of dimensional analysis for simplifying the fluid dynamic problem. And then I will introduce the advantages in data generation by using dimensional analysis, and the advantages in the data presentation. And then I will make an introduction on the conventional non-dimensional parameters in fluid dynamics. For dimensional analysis, the most used example is the smooth horizontal pipe of a diameter d with the fluid velocity v. And we assume the fluid density ρ and the fluid viscosity μ. The question is to find how the fluid friction will change in terms of the environmental parameters, that is, the fluid velocity v, the diameter of the pipe, the fluid density ρ, the fluid viscosity μ. By using the dynamic analysis, the dynamic problem of 5 physical parameters, the expression of the problem is the fluid friction Fr as the function of the fluid velocity v, the diameter of the pipe, and the fluid viscosity and the density. By using the dimensional analysis, we can reduce the problem to two non-dimensional parameters. That is, the expression of 5 parameters would be given as the relation between these two non-dimensional parameters, the friction on the left-hand side, and the Reynolds number as the parameter of the function. This means the friction Cf is only dependent on the Reynolds number. In such a way, the fluid dynamic problem is much simplified. Now we look at how this dimensional analysis could simplify the problem. The first discussion would be on the experiment studies on the problem. In the case of the smooth pipes, the original multiple variable problem is given as this. And after the dimensional analysis, the problem is reduced to the relation between these two non-dimensional parameters, Cf and the Reynolds number. So, for studying the problem in the direct fluid dynamics, we need to change the fluid velocity. This is easy in the experiment. And for the relation between these two non-dimensional parameters, this can be also done by changing the fluid velocity. This is easy again. If we want to change the pipe diameter, it would be difficult in the experiment because we need to change the model for the experiment. And if we have to examine many pipe diameters, we would have many models for testing. However, the problem can be easily solved after using the dimensional analysis. For instance, for Reynolds number doubling the pipe diameter, that means we need to double the Reynolds number. However, this can be done by double the fluid velocity. Thus, we don't need to change the pipe diameter. Instead, we can change the velocity of the fluid in terms of Reynolds number. And if we look at the friction coefficient, change the velocity and change the diameter would have similar effect on the friction coefficient. If we want to change the fluid viscosity, this sometimes could be difficult if we need to change the testing fluid. For instance, if we double the fluid viscosity, And we can achieve the same change of Reynolds number by halving the fluid velocity. In terms of the fluid friction, this can be done by changing the fluid velocity. If we double the fluid density, again it's difficult since we need to change the fluid. For instance, if we double the fluid density, that means we double the Reynolds number. And we can achieve the same Reynolds number by doubling the fluid velocity. So we can see after dimensional analysis, all these changes can be done simply by changing the fluid velocity. This would simplify the test very much, and this is the principle for most model tests in fluid dynamics. The second discussion would be for data collection by numeric studies. So again, the original multiple variable problem given by this, and we need to at least change 3 of the incoming velocities and 3 diameters of the pipe and 3 fluid viscosity and 3 fluid densities. Although in numeric method we can change these parameters easily, the question is, every time we change this, we might need to solve the Navier-Stokes equation, and it would be very time consuming. So the total case would be equal or larger than 3 times 3 times 3 times 3, 81 cases. However, after non-dimensional analysis, we can achieve this by changing 3 different incoming velocity and achieve the same effect for changing the diameter, changing the fluid viscosity, and changing the fluid density. So in this case, the total case would be only equal or larger than 3, so we can see the much reduced cases from the direct fluid dynamics to the case after the dimensional analysis. Of course, for practical purpose, the cases would be much more larger than 3 for the cases after the dimensional analysis, and it would be many more cases than 81 in the direct fluid dynamics. The other problem for the direct fluid dynamics is in the data presentation. In the direct method, we need to put the data in this form. Here, it's for one fluid density. So from the plot, we can see for one fluid viscosity mu1, we have the drawing the fluid friction against the fluid velocity. And we can see here we have 3 different diameters of the pipe, D1, D2, and D3. So if we change the fluid viscosity, mu2, we have another similar drawing given here, and for mu3, we have yet another drawing here. This is the plot only for one fluid density. And for the second density, we have a similar plot. And for the third one, we would have another plot given as this. And even we have the plot like this. And then when we try to get the fluid friction, if the environment parameters are given, for instance, V, D, mu, and rho are all given, so we need to get the fluid friction. So what we can do is, first step, to reduce the multiple plots given as this into one plot for the corresponding density. And then we can reduce the multiple curves on V and D by interpreting the fluid viscosity. And then for the given D, we can obtain a curve on V. And finally, for given V, we can obtain the fluid friction. So we can see the process for getting the fluid friction is also very complicated. If we use the dimensional analysis for the data presentation, we would have the curve as this, the friction coefficient CF against Reynolds number. So this is only one curve. And we can see from the curve, this part, when Reynolds number is low, for instance, less than 2,300, and the flow would be laminar. So this would be given as the red curve. And when Reynolds number is larger, the fluid would be in transition. And for the fully turbulent flow, the fluid friction coefficient would be a constant C here. It is also noted we can see the fluid state, laminar or turbulent flow, is depend on the Reynolds number. From this plot, we can clearly see when we will have a laminar flow, a fully turbulent flow, and this is not fully dependent on the individual parameter. Also, from this curve, for the given environment V, D, mu, and rho, using the dimensional analysis, we can calculate the corresponding Reynolds number Re given by this formula from this given parameters, and find the corresponding friction coefficient CF from the curve once the Reynolds number is calculated. And then we can easily calculate the fluid friction using this equation. So we can see with the dimensional analysis, it is much easier to present the data as well as to find the fluid friction if the environment parameters are given. Now we look at the more practical problem, the pipe with the roughness. The function of the fluid friction Fr would be given as this. The function of the fluid velocity V, the diameter of pipe, the fluid viscosity, the fluid density, and the pipe wall roughness R. Now, this is a dynamic problem of 6 physical parameters. And using the dimensional analysis, we can see N would be 6, and M, the number of base unit, would be 3, same as before, because the roughness height has a unit of meter. Thus, the base units are not changing. And then we have P equaling to N minus M equaling to 3. That means this problem would have 3 non-dimensional groups, pi 1, pi 2, and pi 3. That means the dynamic problem is reduced to a dynamic problem of 3 non-dimensional parameters. And the dimensional analysis would give the formula for the relation between these non-dimensional parameters. The left-hand side is the friction coefficient, and this one is the Reynolds number as we have seen before. And R divided by capital D is the relative roughness. Or we can express the equation as CF equaling to F2, RE, and epsilon. Now the problem is friction coefficient is dependent on the Reynolds number Re and the relative roughness. If we draw the data for the fraction of the flow in the pipes with roughness, we will have a drawing called as the Moody diagram. So this is the drawing for the fluid fraction for the pipes with roughness. And we can see for the laminar flow, the fluid friction coefficient is dependent of the pipe wall roughness. And for the fully turbulent flow, the friction coefficient CF would be constant, but for different roughness, we have different curve C here. And for transitional flow, we can see the changes of the friction coefficient. So for getting the fluid friction from this Moody diagram, we have the steps like this. Step 1, calculate the Reynolds number. And step 2, calculate the relative roughness epsilon. And by interpolation on Reynolds number and the relative roughness, we can obtain the corresponding friction coefficient CF from this plot. And then we can calculate the friction from the formula as this. So we can see by increasing a parameter in the problem is much more complicated. And if this has to be done in the direct flow dynamics, it would be much more complicated because we include the additional parameter, the roughness of the pipe wall on the fluid friction. Now in the next two slides, the long-dimensional parameters in fluid dynamics would be presented. Here in this slide, we can see for the physical quantity force, we would have the force coefficient given by this, as we have already seen for the fluid friction. And for the physical quantity, viscosity mu, it is corresponding to the Reynolds number Re given as this. And for the pipe wall roughness or the surface roughness, we would have relative roughness epsilon given by this. Here, we see rho is the fluid density, V is the fluid velocity, L is the characteristic length, such as the diameter of the pipe or the chord length of airfoil. And S is the reference area, such as the surface area of the airfoil. For instance, for airfoils, the lift coefficient CL and the drag coefficient CD would be the special cases for the force coefficient. Take the airfoil, for example. We see the lift coefficient CL is depend on the Reynolds number. See here, for different Reynolds number, we can see the different curve, as well as the drag coefficient CD. Here is against the CL as a conventional expression in the force for airfoil. So again, we can see the quite a big difference for different Reynolds number. And in here, more non-dimensional parameters given. For the pressure, we have the pressure coefficient Cp given as this. And for the moment coefficient Cm is given as this. And for the speed of the sound, A, we have Mach number m infinite defined as the incoming flow velocity divided by the speed of the sound. The Mach number is very important when it is close to 1 or larger than 1, such as in the transitional flows, supersonic flows, and the hypersonic flows, in which the fluid compressibility becomes very important in the fluid dynamics. And for the gravity force, this is very useful in the wave structure interaction. And the corresponding non-dimensional number is the fluid number, Fr, given as this, and more. And in the future, in my talk, we will use all these non-dimensional parameters for fluid dynamics. For example, if we examine the pressure distribution on the airfoil, normally we will give a plot like this, the pressure coefficient against the relative position on the airfoil. We hardly give the direct pressure from our study. And here, one physical quantity called dynamic pressure, Q equaling to half rho V squared, or Q infinite equaling to half rho V infinite squared. We have seen this in the definition of the force coefficient definition. Because of the advantages of the dimensional analysis in fluid dynamics in both hydrodynamics and aerodynamics, all the physical parameters would be more likely given in the form of non-dimensional parameters rather than the direct value of the parameters, such as the coefficient in the last and this slide.